So in this video, we're going to look at how to change the limits of integration in 2 dimensions, and then we'll save the 3-dimensional cases for a follow-up video. So we're going to start with an example. We have an integral that's from -1 to 1 in the x direction and from x squared to 1 in the y direction, and we want to change that order of integration from dy dx to dx dy. So let's look at how we break down what this means. So because the inside integral is integrating in y, our 2 inside functions are y equals 1 and y equals x squared. So those are our 2 limits of integration in y. So those are expressions in y. On the outside, we have x equals 1 and x equals -1. Now, we can't just like switch them because there's a function here. And that means that you can't have functions on the outside integral. You can only have them on the inside integrals where you haven't integrated that variable yet. So the only way that we can really do this is to draw the graph that represents this combination of expressions and then switch it graphically. So it's not mechanical. It's not like we can just make it up and do it really quickly. This is the process. All right, so let's draw our graph. So here is our y equals x squared, and here's our y equals 1, and the intersections are the -1 and 1. That's where those boundaries come from. Now, in order to change the order, we need to change our y equals x squared into x as a function of y. And so when we do that, we get boundaries on this side as y equals the square root of x, and on this side, y equals -square root of x. Y equals 1 is still there. Now, when we are doing x first, we have the left side as the bottom limit and the right side as the top limit. So y equals the square root of x is our top limit in our integrating in the x direction, and y equals negative square root of y is the bottom limit because that's the leftmost edge of our graph. And then the dy, we're going to look, what is the range in y? Well, the bottom of our square roots is at y equals 0, and then the other boundary is this function y equals 1. So that's our 0 and 1 here. The function itself doesn't change in this example because all we're doing is switching the order of integration. But we cannot just switch the order of the limits if they're not all constant. If they're all constant, then it's just a rectangle. There's no dependency on the other variable. But when there's a dependency on one of the variables, you have to draw the graph. Now let's consider another example. So here we're going to switch the order of integration in order to simplify, because integrating ln y, it requires integration by parts. So that's no fun. So let's look at our graph. So we're integrating x first. So ln y, when we write that down and we solve for y, we get y equals e to the x. So that's this red line here on our graph. We also have x equals 0. So that's this line right there. On the other integral, we have y equals 1, which is right here, and y equals 10, which is up here. Now, this y equals 1 represents the intersection of x equals 0 and this curve y equals e to the x. So that's just the result of an intersection. It's not like an extra boundary. But what it does is it confines us to this region right here, where the arrow is pointing. Now that we've rewritten our functions, now we can think, okay, if dy has to be on the inside, what's the top and the bottom function? The top function is the y equals 10. The bottom function is this exponential curve. And then on the x direction, we're going from 0 to where this exponential curve intersects with this line. And when 10 is equal to e to the x, you can solve that for x is equal to log 10. And so that is our rewritten integral, still in x and y, but now in dy, then dx, instead of dx and then dy. Now, the third example that we want to look at is rewriting in terms of polar coordinates. Now, this is a complex and messy integral because we are trying to do something that should be in polar coordinates and writing it instead in terms of rectangular coordinates. And so we want to keep in mind that we're trying to find essentially the volume of this region. It's all one region, but because we're in rectangular coordinates, we had to separate it into two integrals. So let's see what kind of boundaries we have. So first of all, the square root of 8 minus x squared, that's an integral for y. So if we set y equal to this and square both sides, we can determine that this is the boundary of a circle of radius 2 square root of 2. And we also, on this side, we have y equals x and y equals 0. And then we have this integral going from 0 to 2, and this one going from 2 to 2 square root of 2. So we start putting all of these on a graph. The first region is this section down here. And then the top one, the second integral, is this region over here. So we're going from 0 to 2, where this y equals x line intersects with the circle. And then the rest of it, so that's a nice rectangle, that's easy. But then the rest of it, the upper bound is the circle, but we're going from 2 to 2 square root of 2, which is the radius of this circle where it intersects the x-axis again. So what we want, if we switch to polar coordinates, we want to be able to do all of this whole wedge in a single integral. So just because we had two integrals before doesn't mean that we're going to have two integrals later. So the y equals x line is going to represent a slope of 1. And when we put that into the inverse tangent function, we get pi over 4 as the angle here. And this angle down here is, of course, 0. So we're going to integrate in theta from 0 to pi over 4. And then the radius, we're going to integrate from 0 to 2 square root of 2 because it's x squared plus y squared is equal to 8. And so when we set up our bounds, theta goes from 0 to pi over 4, and radius goes from 0 to 2 square root of 2. But because we're switching to a completely different coordinate system from x and y, we have to change not only our dA to r dr d theta instead of dy dx, we also have to change our function. Now, the original function was xy. So we're going to replace x with r cosine theta and y with r sine theta. And when you do that, you get r cosine theta times r sine theta times the extra r from the r dr d theta. So that's 1r, 2r's, 3r's, r cubed times sine theta times cosine theta. And now we have our integral set up and ready to go for actually integrating. And we're only doing one integral and not two. We'll pick up the three-dimensional case in the next video.